Okay, so today we will finish our TCP by two things. One is we finish our congestion control. Last time we have already done the congestion control for Tahoe and Reno. Tahoe and Reno. And today we will deal with some threshold. So we do the Tahoe and Reno with the threshold. Why we need this threshold? Because you have the slow start, right? So at the beginning, I do 1. So the start, I will do 1 ms maximum segment size. So MSS, so maximum segment size. Okay, so this one is beginning. I do this. Then if I got acknowledgement back, then I will do 2 MSS, right? 2 MS, 2 maximum segment sizes. So 2. Then if I got acknowledgement back, okay, that's good. So MMS, okay, I will do double the size. So every time I will double the size. Until I got a certain kind of, if I do 16 MSSS, so then that looks, so this one, if every time I got a ACKs back, then that's great. But you may find some problem is every time I double the size, then I take more and more risk because I make the network become more and more congestion. So at a certain point, so for example, at this time, I may have issue. So this issue is I may lost some ACKs. So ACKs. So maybe it's a 3 double ACKs, or it may be another thing is I just lost the packet, some segment. So then this time, no matter Tahoe and Reno, it will make the decision, okay, this is the congestion happens, right? Congestion happens. But you lost a lot, right? This one, because I start from 16 to 32. From 16 to 32, so I have 32 segments sent out. If I lost, because make sure that our TCP is go back end, right? We do the go back end solution. So this one is, I may lost a lot for that segment. So what we do is, okay, we should do another thing. So we call it politely increase the congestion window. So not like this. This is slow start, 1, 2, 4, 8, 16, 32. I want to do politely increase the congestion window after certain window size. Instead of I jump that much and push a lot of segments into the network. So we will introduce the things we call it threshold window. So threshold window. Okay, so this is the threshold window size to say that, okay, below, this one is below the window size, this window size, below the threshold, we do slow start. Slow start. Means we still do 1, 2, 4, 8, 16. Okay. And above the threshold, we increase our congestion window linearly. Okay, so there we introduce the threshold so that we will do separate. So what does it mean? So let's still use this as an example. So we have 1, 2, 4, and we say that our threshold is setting. So for example, our threshold setting is 10. Okay, so if our threshold size is 10 MSS, then what we will do? So the scenario will be, I will do 1 MSS, so 1. And then if I get all, so I will do 2 MSS. Okay, and then, where's my whiteboard? Okay, so here. If I get correctly, I will do MSSS. So then 8 MSS. Okay, if I all get the feedback correctly, then we look at our previous example, we do 1, then 2, then 4, then 8, then 16, then 32, right? This time, I set the threshold size is 10. So instead of go to 16, I will do 10 MSS. Okay, so this is 10 MSS. Then if I still get a success, so I will do 11 MSS. So then this one is increased linearly instead of do double size. So it will be 12 MSS. So it's a continue until to some kind of place, for example, at the 12 MSS. So I got some loss of ACKs, then it will go. So say that, okay, I got some loss. I got some loss. Then the algorithm will say that, okay, since I got some loss, so what does it mean? It means that I got a congestion, get some ACKs loss. So then I will set the threshold. Then the threshold size will be set to 6 MSS. Okay, so this means I will reduce the size to be the half of the current maximum segment size. Okay, so this is the whole picture. We deal with the threshold involved. Okay, so now let us see an examples in the slides. So let me see, where is my example? Okay, here. Close. Okay. Okay, so let us see. This is our example. So at the beginning, we first look at the Tahoe. So the Tahoe one, we start from 1 MSS, then double the size, double the size, double the size. If our threshold window is 8, so when I approach 8, then it will go to, it will increase the size one by one. So it will be 9, 10, 11, 12. So at this moment, I got some loss of ACK or duplicated ACK. So Tahoe will do the things is I directly go back to the beginning, right? So if no matter you lost or you have 3 duplicated ACK, you will jump back to 1. So it will jump back to 1. So it will be like this. And your threshold will set up the half size. So this here is 12. Here is 12. And this time my threshold will set to 6. It's the half size. Okay, so it's reduced to 6. So my Tahoe will do is increase, slow start is 1 to 2, then to 4. Now the next jump will be 8 if you get ACK correctly, but since my threshold is set to 6, so it will jump to 6. Then it will increase a little bit one by one, so linearly. So the congestion window will do linearly. So then 6, 7, 8, 9, 10. So until I have 3 duplicated ACKs or I lost ACKs, so then it will give me, it will jump back to 1. So the graph is more likely, it looks like this. So what is the Reno? Reno have the 2 cases, right? If you have duplicated ACKs, it will not jump directly to 1, it will jump to here to the threshold. So your threshold is from 12 to 6, then your jump back is directly half the size, half the window size. So it will still be the 6, right? So the same. So the 6, then it will do the linearly. But if Reno meet, if you lost the ACK, means the segment has been lost, then what it will do is it will looks like the Tahoe, so it will go back to 0. Go back to 1. So it will be, this is the, so for TCP Reno, you have 3 duplicate ACK, it will cut in half window, right? So if you have the lost ACK, then you will go back to 1. Okay, no matter you do Reno or Tahoe, so it will go back to 1. So duplicated means that you still can deliver some segments, but you cannot deliver the whole thing. So this one is the congestion. Okay, so this is the general for the TCP to deal with the congestion. Before I analyze the performance of TCP with the congestion control window, I should summarize that. So we have 2 windows, right? One is the receiver window, right? This is the receiver window, is the receiver side to tell the sender side how much you can send. This means that how much buffer I have at the receiver side, right? This time we also deal with, this is for the flow control. This is the flow control. And this one, we have the congestion control. So the congestion window, this one is for the congestion control. So for the congestion, I have another window to tell the sender that this one, how much you can send to the network. So I have these 2 windows. So my question, so the question associated is, should we implement these 2 windows separately? Do we need to maintain 2 windows? Think about this question, 2 minutes. Anyone can answer to me? Actually, the answer is no, we don't need to maintain this 2 windows, but actually we just create 1 window at the sender side because this window size is maintained at the sender side. So the sender side can look at, okay, what is suggested by the receiver, how much I can send, and what is the congestion window this time I can send out the packet out. So this one, finally, you will just have 1 window size. This one will be equals to minimum. So this 2 window size. So this one is the receiver window. The other is a congestion window. Which one is smaller? I will use it to send out my. So this one is final your window size. The window size is determined by these 2 windows, but you will combine them together and make the minimum one as the dominate. So if my network performance is worse, then congestion window will dominate my window size. If my receiver side has a limited buffer, then the receiver window will dominate the final window size. So this is what we have. Now we move to the next one is what is the throughput? Previously, if you do the IP stuff, you don't consider about the reliable transmission, you don't consider the congestion control, you just send out the data. So you try to fully occupy the data link. If you have the space, you just let me send out. But this one, you know that this will not be a good idea because in the network, too many traffic goes into the same router will make a congestion. Also, the receiver side may not have enough space to hold that one. So we need to analyze with the TCP, what is the average throughput with TCP if we have the window size. Before we do the analysis, we should make some assumption. We ignore the slow start. We assume always data to send. So if I have data, I have data to send. And then the window size where the window size is measured in bytes and where the loss occurs. So this one is average window size. So we don't consider a slow start means we use Reno and we always have some space to send out the data. So we use Reno. So Reno means I got 3 duplicate ACKs. I don't consider the data loss. Okay, so this one is what we do. We make our estimate a little bit easy. So I can increase my segment into W. So the W here is the data loss. So you have data loss here. But you can do is, okay, at to here, I just go back to half. So like the Reno, so we go back to half. And then we increase and then like the Reno, right? So we increase linearly and then jump back to half of the size and then increase linearly, then jump back to half. So if this is the case, then we know that this one, the average throughput will be 3/4 of the window size over the RTT. So the window size is the bytes, RTT is the segment. So this one is the average throughput. So this is, we can see that how we increase our throughput. The way is, okay, we reduce our RTT. So reduce RTT, how do I reduce RTT? One way is we are close to each other. So if we close to each other, then our round trip time will be shorter. Or this close also means that you pass fewer routers, then it will be close to each other. So you don't suffer too much congestions at each router, so you have lower chance to get data loss. So this one is remains close to each other. Then another thing to increase my data throughput is increase my window size. So the window size, I want to make it bigger, right? So the window size bigger, then my throughput will be larger. But this one is estimated under the scenario which the network is not a high-speed network. So in the high-speed network, this one is very long and flat pipes. So we have 10 gigabit per second throughput, want this throughput, and our round trip time is long, so 100 milliseconds. But our segment is very large, so 1,500 bytes. Then, if we want 10 gigabit per second, then this one, the new throughput for the high-speed network will be 1.22 times maximum segment size. This one usually is 1,500 bytes, and the RTT over the square root of L. So this one is the loss probability of loss probability. So if we want to achieve 10 gigabit per second throughput, then we need a very, very low loss rate. Okay, the very, very low loss rate. So 10 to the power negative 10. So this is quite small. So then what we need to do is we need a new TCP for high speed. So new TCP for one thing is called, so the high speed network. So the high speed network, for example, for the optical network, so our capacity usually can be beyond 10 gigabit per second quite easily. So we need to modify our TCP. So this time, I will erase. So this time what I need to do is I need to modify our TCP. So to hop TCP. So we call it a hop TCP, hop by hop TCP. So what does it mean that instead of point to end to end, so you cross multiple routers, I just one hop from the first hop from the router to the next router. I do the create TCP. So it's a hop by hop TCP. Then hop by hop TCP can achieve the low RTT, the low small loss rate, and it will be easy to control and do the retransmission. But what is the question for hop by hop TCP is that this hop by hop TCP, you may suffer too many versions of TCP and cross over the router and TCP layer. So this one is a little bit headache, but to accommodate high-speed network, you may modify your TCP level to the hop by hop TCP. Okay, any questions? Okay, so the next one, we want to measure the fairness of TCP. What is the fairness? The fairness goal is try to make sure that if I have multiple TCP sessions share the link, I want it to be fair to everyone. So everyone will get the, if I have K sessions, everyone will get the bandwidth over K is finally achieve this fairness goal. If assume that this TCP sessions keep sending data. Okay, so this one is not like what we do is FDM or TDM. So this one is partitioned and guaranteed fairness among the users. TCP sessions, you based on the window size, and I don't know for the other session what the case of the other session. So this one is more dynamic. It's not a static partition. Now then we need to adjust whether it's fair to every session or it's not fair. So how do we know it's fair or not fair? So we need to draw a figure. So the figure is looks like this. Okay, suppose we just have two connections. It's quite easy. So what is the window will do? So you will do the congestion avoidance, additive increase. So you increase your window size, but you will decrease by half, and then increase, and then decrease, then increase, then decrease. So finally, you will approaching the equal bandwidth share. So if you go beyond, then you will go back half, and then you go beyond, then go back. So by this analyze, we know that finally they will achieve, if they keep sending data, finally they will do the equal bandwidth share. You can through the queuing theory or stochastic processing to analyze mathematically, but this is the picture. This is the picture when we deal with this congestion window. You try and make it bigger, then you get you get 3 duplicated ACK or you get loss. So you will have the size go beyond this. And then finally you increase your data size and you will finally approaching the equal bandwidth sharing. That's why we say that TCP is fair to every session, Okay, that's for the TCP congestion. Any question? Okay, if there's no question, then we move forward. Is the last thing associated with TCP before we move to the socket programming. So this thing is how we maintain our connection. So this connection, we do the TCP connection. We say that okay, we can do congestion control, flow control, and reliable deliver a data transfer. Then we have still one thing left is how do we establish our TCP connection? Then how do we tear down our TCP connection? So these two questions is later we will do the socket programming. It will be hidden inside, but this time I will discuss through this couple of slides. So think about how we set up our conversation between two guys. So actually, I would just say, hello, can we talk? Then the other guy say, hey, it's okay. So now we can talk. So what is this connection? This connection is established through two-way handshake. So two-way handshake, so we do this for the network if we do the TCP. So the client, so the computer here, so the computer here say, hey, can I set up the connection with you? Then the server say, okay, you can establish a connection with me. So the question is, will two-way handshake always work in network? This one, we think about what is same thing and what's the difference. So we can do face-to-face conversation through two-way handshake because we know that the delay is limited. So when I speak to you, I know that after several seconds, you will get this message. Or if we do face-to-face talk, I talk to you, usually you can get it immediately. So the delay is manageable. Then, second one, I talk to you, I will not talk further until you say it's okay. But in our network scenario, the message may reordering. Your delay may be different. You may retransmit the message due to the message loss. This message loss you retransmit actually may not totally loss. It may be reordering. The big problem which we cannot use two-way handshake in our TCP connection is two sides cannot see each other. So the computer here cannot see the face of the server. Means the server give me some hint to say we can talk, or it's listen to me. So the computer here does not know whether the server listen to me or it gets my message or not. So this one is a kind of a headache. So let us see the example for two-way handshake may fail. So this one is the original one, right? So I send out the request and accepted by the server. So suppose this acknowledgement is late, it's timeout. So I will send out another request for connection. And this one suffer very, very long delay. And this one, the delay is still long, but it's not that long, so it's established. Then when this new connection, actually this is not a new connection, this one is just a retransmitted connection request comes, the server forget this one is the X. So because it's already closed, terminates. So this one is half open connection, right? So this one is no. So if I have the data, this one is I retransmit, and if the data is also retransmit, then this one will be accepted at the server side. This one is okay, but this one you accept the data which is not belongs to this connection. If this one does not belong to this connection, this data x+1, data x+1, we call it's leaky because you are not belong to this connection. This one will be very, very bad if you have certain usually when you set up the connection, you will do what is the first message you will do. Your first message is probably is your user ID, right? You will provide your user ID or you provide your username. So this one is not good. You leaky, you make this information leaky. This one is the server has already finished this connection and it get the new data and treat like a new data. But this one is the retransmit one. So this one is not good. If we do two-way handshake, we have some failure happens. So now in our TCP, we do the three-way handshake. So what is the three-way handshake? Client state and the server. So client will use the synchronized bit to indicate it want to set up the connection. So this is a synchronized bit. So still remember our TCP segment. So we have one is called a synchronized bit. So this synchronized bit is one means you want to establish the connection and with the sequential number X. Then the server side will acknowledge it with the sequential number Y and put the synchronized bit 1 and the acknowledgement number will be X plus 1. Until this time, it's not established the connection. This established will be the client side will say, okay, I acknowledgement bit is 1, and to say, okay, I got your acknowledgement and my acknowledgement number is Y plus 1. After this time, then the client side and the server side establish the connection. So now this is one way, two way, third way. Oh, you may think about that if I get a time, if I at the two-way handshake, if I get a timeout at here, I do the retransmission. Then this retransmission is synchronized bit equal to 1. This one is sequential number is X. So later when you do the sequential number after this termination, this new things comes, then the server will ignore that because you have sequential number X, right? The server Y doesn't know that this one is the synchronization bit. So this one is a kind of thing. Now, when we want to tear down the TCP, so the next one is how we close a connection. Close a connection, different from the synchronization, say the open a connection. Close a connection, we try to make sure that when we tear down the connection, we want both sides finish the transmission. So we should wait for a while. So let us see what happens. So this one is a client socket want to close. We'll have the finish bit that is equal to 1. So means I want to finish the socket. Then server will acknowledge it, but make sure here, it cannot close the socket immediately. So it will do the close wait. And this one can still send the data, so the server may still have some data to send out, okay? So the server send out the data until it give you the finish bit equal to 1 and the sequential number. So say that at the server is no longer send data anymore. Then it will send out to say, okay, I will not send any more stuff. But the server side, both sides will not end the socket. Why? Because the server side need to receive ACKs from the client side. So you finish sending doesn't mean that you get all ACKs from the client side, right? It may still have the duplicated ACK or it may still have the data loss to the client side. So at this time, it will no longer send data, but wait for the ACK bit back. So the client, if it gets the ACK from the client side, it will close the socket at the server side. And the client side will wait 2 times of the segment lifetime in case some data will be still come to here. Or it will, for the ACK is not received by the server, it needs the time to ACK again. Right, so this one, if it's not get by the server time, so it will ACK again. So it will wait for 2 segment lifetime, and it will close, means that this ACK suppose is already received by the server side. Okay, so then it will close the socket. So this is the closing. Any question about the establishment and closing the TCP socket? Okay, if no one has the problem, then we move to the next part is our socket programming. So today I will discuss a little bit about the socket programming, and then through one example, and then next class we will go back to look at to summarize our examples. So to give you the key concepts if you want to do socket programming. Okay, so let us, I will share the screen. Where is my share? So share the screen, NetBeans. Okay, so this is the example of Echo server and Echo client. Okay, so here, when you do the socket programming, you should write 2 portions. One is called server side, one is called client side. So this one is actually means we deal with socket programming based on the client server model. Okay, well, we discussed 2 models we'll discuss these 2 models in the operating systems. But here, I can do a little bit introduction for the client and server model. So client and the server model is more likely the older version. So previously, when you want to get some service, then this service is maintained at the server side. And if you want to get the service, then you will go to that place and get the service, and you are the client. So a good example for the client server model is, think about the bank. Bank is the server. You are the client of the bank, right? If you want to do something, for example, if you want to deposit or you want to withdraw some funds from your checking account, you should go to the bank. And this bank will provide the service to you. So bank hold all kinds of service related to the bank, related to checking or saving account. And then you are the client and go to the bank to meet the tailor. Tailor is the server to serve. So our socket programming is also a client based on the client and the server model. And our client and server model, if we want to do the network programming, the first thing you should import is the network package. So this time, this is the network package. And of course, you want to do read and write. So you read from the socket and write to the socket. It's more likely you do the standard I/O. So you should have the I/O package. Okay, you should have an I/O package so that you can do the reading and writing from the socket. So for the socket, we first look at the server side, and then we look at the client side. Before we do that, here is some information associated. Now, if you deal with the socket programming, the server side is the passive socket, which will first be created and wait for will be first created. So the socket side, so the server side will be first created and wait for connection, wait for the client to connect. Think about you do the bank, right? The bank is the server. So the bank should be first established, then you can have the client. So this is the same thing. If we do the server, we do the socket programming, the server side should be first created. This way, why we call it a passive socket. The passive socket means that this passive things means you wait for the connection. So just like a bank, if there's no client, so even if there's no client, the bank should be open, right? So this one is the passive, wait for the client. And then client side is the active socket, which will be created as needed and connect to the server socket when it's available. And will connect to the available server socket. Okay, so if you run the client side first, then there's no server side, then you cannot make any connection, you will get exceptions. So this means client server or client side will create later. Okay, so if you don't have the server side, then you will get the exception. Right, so this is the fundamental idea. And now we look at the server side, what we need. So the server side, we should create a server socket, and this one is the server socket. So in Java, it's quite easy. You just create a new server socket, and this server socket, the passing is the number is with the port number, right? We have already learned in TCP, so we have the port number. So this port number can be any number, any integer number, but this one, my suggestion is in your homework or at your group project, you should be use some port number which is not well known. Of course, you can use 80, but this one is not good. And then when this guy's, what's the work associated with the server socket? So the server socket with the port number, so actually the Java virtual machine will create the server socket, with port number and IP, the current IP address of the server. So the first thing Java virtual machine will do is create a server socket with this with the given port number and the current IP address of the server. So this is the first step. Then the second step, Java Virtual Machine will bind the port with the IP address. Since I don't give you the IP address at this server socket, so it's the server its own IP address. Then the Java virtual machine will bind the port with the IP address. Okay, this is the binding. So we call it binding procedure. Okay, this is the binding procedure. This is the second. Okay, so the second portion and the third portion, the socket. So this one, if you bind that, then server socket has been done and listen to the channel. Okay, it will open the channel and listen to that. So listen to the port. So listen to the channel. Actually, it's listen to the port. Right, you have the port, so you listen to the port. And for server socket will wait until a client socket connection is coming. Okay, so it will keep waiting. That's why we call it passive. So that's why we call it passive, because it's wait until a client socket connection is coming. Okay, so this is the whole thing when you generate the instance of the server socket. Then when the client socket comes, this one is the server socket accept the client connection at here. So you use accept to accept it and create an instance. Create a variable to indicate the client. So here I use the client socket. Of course, this one is the socket. Okay, I declare it here as the socket. So it's not the server socket, now it's the socket. So for the socket, actually you can declare any name for that, but it's create a variable. Here I call the client socket, and then to indicate the client. So it looks like a pipe. You have two connections. One server connect to that pipe, and the client comes, and then they set up the connection. Okay, and then the remaining is, if this one is accepted, then your connection is successful. And then you can just through the read and writing, just like the read and write a file. So same thing, you can read from the socket or write into the socket. So this is the server side. Server side, the key concept is here. So you use new to create the server socket, and this one you should do it at the beginning, and this one will do the 4 steps work. And next is when a client socket connection is coming, so it will accept the client connection. So use this method, server socket dot, so the method is called accept. And then you create the variable to indicate this client socket. So the client one. So to indicate the client, not the client socket. So it's indicate the client. And when you set up this connection, now you can do is just like the read and write from or write to the file. So it's the same thing. Okay, now let us look at the client side. So here is the client side. So the client side should give me the server host name. So this is the client socket. So you create the socket here. So the client socket. So this one is the client one. So in is client socket. Okay, so I create the echo socket means I create the client socket. So this client socket, what it will do is first, this is the active, so it should know client socket should provide the host server host name. So server host name, it can be IP address. In here, in this example, we use IP address here, 127.0.0.1. Actually, it means myself. This is the server and the client are at the same machine. So if you know the server at a different machine and has the IP address, you can put it here. So this is the other IP address. So make sure that this IP address, if you are not at the same network segment, so you should know the public IP address. So then the second one, you should know the server socket, and you should know another, should provide the and IP address of the server. No, not the IP address, the port number. The port number of the server. Okay, it should first know, so this one, my server side, the port number is 12345. So this one is the port number. And the client will try to connect to the server. If succeed, then your echo socket will get this information. So to refer to this socket, so the client socket means it connect correctly. So you can get the output stream or input stream to the same file, like a file reading and writing. If it's not, then it will get a certain kind of information is you don't know the host. If the host name is not correct, then you will get the host unknown host exception. Right. So if the port number is not available, you will get the unknown host exception. So this is for the client side for the socket. So the client side is quite easy. It's no that big chunk of waiting because it's active. So it's active. The server side should already should be there. So otherwise you will get exception. So that's all for the client side. This one is quite easy to connect. And then the remaining things is just read and write the file. I put this Echo client and Echo server on the Blackboard so you can download and look at the code. And run it. Make sure when you run the code, you first need to run the server side. So the server, because it's the passive one. You should create a bank before you can accept the client, right? So then you can run the echo side, so the client side. So this is echo, so you will see that the connection successful and waiting for the input. So this is echo means client type something, the server get, and then echo back. So I type in aloha. So the server side will say, okay, I get the aloha and the echo back. So it will get echo back. If I type bye, it will be bye. So the server side will say bye and close the socket and it will say echo back by, and the socket will be closed, so it closed. Okay, so this is a simple demo for the socket programming. And the next class, I will do a little bit, elaborate a little bit on the socket programming. This one will be used in your project 1 as well as project 3. So this is a fundamental demo for you to understand how to do the socket. Okay, any question? If there's no question, you can talk with your group partner to set up the timeline for your group project. Remember, this time, I think this is the, we have 2 more weeks. So 2 more weeks for lectures. So you should finish within 3 or 3.5 weeks. So make sure that the time is a little bit tight, and you should start as early as possible. Oh, the question, you will have another homework. Since since project 2 does not require socket, so you will have the last homework for the socket program. Any other question? Okay, then that's all for today's class, and see you Thursday.